Then it's a pleasure to have Joanna Luc presenting about what spacetime does. Please.
Okay, thanks. Here is the plan of my presentation. It is very simple. So first, I would say something about spacetime functionalism in general and how I understand it. Next, I will provide some possible classification of functions of spacetime, and my last point will be analysis of relations between these functions, and I would like to ask the question whether they are independent and whether some of them are more important than the others. So first...
Sorry. You'd like to switch off those? Just those, yeah. This is too long. Sorry, it's not possible, sorry. Sorry, shoot.
Okay. So first, the problem for which spacetime functionalism can be useful, as we have already discussed, is as follows. We have different physical theories that are somehow similar to the theories that we already know, but the relationship between them is complicated. So we can ask which structures in these theories can or should be identified as representing spacetime. And one possible approach to this problem is spacetime functionalism. What is the content of this proposal? So to present it in a slogan way, it says that spacetime is what spacetime does, and it can be contrasted with some other proposals about the nature of spacetime, namely container view, that the spacetime is simply a container of matter. With it is also contrasted with building blocks view, namely that what is important for the nature of an object are its constituents, and also perhaps it can be opposition to structuralism, but it depends of our understanding of what structure is. To put it in less slogan way, functionalism in general says that identity of an object fully relies on its functional relations to other objects. I should stress that functionalism and spacetime functionalism is not my idea, and in this talk I don't want to argue for it nor against it, but I only ask myself a question: if I were a functionalist with respect to spacetime, what function would I assign to it? And during this talk I will provide the answer. First I will describe how it seems to me a person who wants to be a functionalist with respect to spacetime should proceed to find what particular function spacetime plays. My proposal is as follows. First, we need some non-controversial cases of space-time theories, such that we know which elements of formalism of these theories represent space-time. And I think that we can agree that special relativity and general relativity are good candidates to place this role, and I will take them as paradigmatic cases of space-time theories. So, to elaborate more about functionalism itself, I understand it as proposing the following structure. There is some relatum 1 and relatum 2 or many such relata, and there are some functional relations between them. And relatum 1 is what is functionally defined, so here it is, of course, space-time. So what should be the second relatum for space-time? I think that in the light of these theories and what we know generally about physics, this second relatum is simply matter in the form of particles or in the form of matter fields. So what we should find, most important part and most trivial part of the whole structure, are functional relations. Okay, so I will start from some general intuitions to provide some general heuristics, what these functional relations are. And after this, in the second part of my talk, I will make this more concrete in the light of, I think, what one can read from the theories which I take as paradigmatic cases of space-time theories. So this general intuition that I propose to start with is that particles are in different positions in space-time, and matter fields have different values in different points of space-time, and all of them in some sense change with respect to space-time. So this, my most general heuristics is that the role of space-time is special relativity, and in general relativity is to give the framework for the description of distribution and change of matter. I have here a little remark about relation of these heuristics to our common intuitions and relativistic physics. According to them, these two rows are more disconnected because space-time is connected with distribution, time is connected with evolution or change of matter. But when we deal with space-time, these two things are not so separate anymore. They form more or less one single function. So now I will try to make my heuristics more precise. So I propose the following classification of functions of spacetime in the light of my heuristics. So first, spacetime as a theoretical object should provide some elements needed to pose the problem of evolution of matter. Here, this problem of evolution includes more or less what I call the distribution of matter in space. Second, space-time provides elements needed to describe properties of solutions of this problem. And third, it provides elements needed to analyze some general properties of the problem itself. Now this digression concerning the first function. From mathematical and physical literature, we know something that is called well-posed initial value problem. Initial value problem is well-posed if these three conditions are satisfied. So first, solutions of such problem exist. It is unique and it depends continuously of the given initial data. And in my understanding of the first function of spacetime, not all of these conditions are needed. I require only that spacetime provides everything what is needed to pose the problem. So some equations of evolution can be formulated, but I do not require that the solution is unique, so maybe some forms of indeterminism are allowed by omitting the second condition, and also I do not include in this function the third condition for well-posed initial value problem. Okay, so what does this first role mean in the context of our paradigmatic theories? So I think that providing these elements needed to pose the problem of evolution of matter amounts to first, providing a location of matter, because particles should be located in some points of space-times, and the same for fields. But also space-time, as we know it from special and general relativity, provides us topological structure, which is needed further to define differential structure. And it is what we need to formulate our standard equations of evolutions. Space-time, at least in general relativity, can have also in this context one more function, namely dynamical function. Because in GR, space-time metric is coupled to matter. First, this function does not appear in special relativity, and of course it is not specific to space-time, because this dynamical function is also possessed by matter fields, so it will be not important for our understanding of proper role of space-time. The second group of functions, space-time provides elements needed to describe properties of solutions of the problem of evolution of matter. So, for example, if it provides the causal structure, namely the division of space-time curves into space-like, null, and time-like, which allows us to describe possible paths of causal influences. it also provides the structure of geodesics, that is division of space-time curves into these that can be trajectories of free particles and these that cannot be such trajectories. And in the third group of function, according to me, we should put the structure of symmetries of equations of evolution, because the symmetries can be understood as a general property of equations of evolution that form our problem of evolution of matter. And in particular, because of the proposal by Alanor that the proper function of spacetime is providing inertial structure, I will comment later a bit about this particular symmetry. So now I would like to say something about the difference between my approach and some approaches that were presented yesterday. I think that my proposal is more ontological in spirit. I would like to compare it shortly with Vincent's proposal and Tushar's proposal. So it seems to me that both of them were less ontological, at least in their motivations. So for Vincent, the crucial thing was this issue of empirical incoherence, and according to him, the function of spacetime should be such that we can somehow resolve this issue. So this incoherence should turn out to be apparent in the end. In Tushar's proposal, we had three functions. We had theoretical spacetime, operational spacetime, and phenomenological spacetime. But if I understand correctly, the main motivation for the first two functions was that spacetime should have chronogeometric significance in order to allow us to use rods and clocks to measure them. So here again there is some important connection to us as observers and as subjects who test our scientific theories, because we need all these things to make measurements to test our theories of spacetime. And also this third function, namely phenomenological spacetime, is of course related to our experience. In my approach, I would like to think about spacetime and about matter as something objective, some objects that in reality play some role, and in some sense they do not care about us as observers who formulate theories and test them. I think that, for example, this issue of empirical incoherence is very important, because if we have such problems, it is surely an indication that something went wrong. But on the other hand, I don't think that the proper function of space-time as an objective physical being, so to say, should be providing something that enables us to test the theories about the space-time, right? So I am concentrating on this objective relations, at least what they look like from the point of view of these theories, which I take as paradigmatic cases of space-time theories. So now I would like to ask the question about status of these different groups of functions. So my claim is that if we agree first with my most general heuristics about the role of space-time, and second with my classification of functions of space-time, then we should also agree that the first group of functions is the most fundamental, and that without it, the other two groups lose their original meaning and the justification of their importance. And the general argument for this fundamentality of the first group is very simple. It is, in some sense, implicitly included in my classification, because according to it, the very existence of the other two groups relies on the existence of the first group, because we must first pose the problem of evolution of matter in order to analyze its solutions or its general properties. So, as you see, this main argument is very simple, and in some sense, my classification somehow begs the question. I would like to elaborate more on this by analyzing some particular proposals of what can count as a proper function of space-time, but all these arguments are more like illustrations, and they do not make my general argument more strong. So first, one could claim that that providing the causal structure is a proper function of space-time. So if one has some structure, for example, of points for which the causal relations are defined, then one could claim that this is sufficient to take this structure as representing space-time. But if one have this, one can ask, okay, this causal structure describes what are possible paths of causal influence. But one can ask why the other paths are forbidden, and at least on the ground of special and general relativity, the answer is that there is some law that has appropriate symmetries And it guarantees us that the evolution of matter will be such that this other path of causal influence this allowed path of impossible causal influence will be never used. Again, coming to symmetries, they are of course always symmetries of some equation, and they lose their original sense if even if there is some equation of which they are symmetries, but it is not this fundamental equation of evolution of matter. How much time?
Still 12 minutes.
Okay. So shortly about the case of inertial structure. I will not analyze it in full generality, but I will refer specifically to Eleanor's proposal, which I assume that assumes at least a general spirit of the description of inertial structure in the work of Harvey Brown. For him, so Brown argues against geometrical explanation and for dynamical explanation of what he calls two miracles. The first is that all laws of nature are invariant, and the second is that the same transformations are symmetry of metric and symmetry of laws of nature. And his answer in the case of special relativity is that simply the problem somehow disappears if we do not take Minkowski spacetime as an independent object, but instead we regard it as merely codification of some aspects of the behavior of particles and fields, and in particular of symmetries of their dynamics. And thanks to this, the metric has a chronogeometric significance, that is, we can measure by using rods and clocks distances in physical spacetime. In GR, one cannot eliminate spacetime in this way, but still this issue of chronogeometric significance is central, and it is again guaranteed by the fact that symmetries of metric and of laws are the same, but in this case we require this only locally, and this is expressed by strong equivalence principle. Inertial structure is the structure of global in special relativity or local inertial frames, and according to Brown, it is important because probably not only, but also because it guarantees chronogeometric significance of the metric. As was, I think, a similar argument was already raised yesterday, that inertial structure is not sufficient for obtaining this chronogeometric significance, and this is because okay, so first inertial structure is connected with some kind of symmetry, and this is symmetry of some equations, and these are equations of evolution of matter, and in the theories that I analyze, these equations are formulated on this very space-time that has this metric, which should have chronogeometric significance. So in this approach, the dynamics is somehow basic, and what I would like to stress is that if we do not have these equations that have this symmetry, or if we have some equations with this symmetry, but they are not defined on this spacetime that has this metric, this whole machinery does not work, so we cannot go from this some form of inertial structure to what we really cared about, namely to this chronogeometric significance. And now again, I would like to stress the difference between what I'm trying here to say and what was said yesterday by Tushar. So first again about the difference between his functions and mine. The functions that I have proposed do not, as such, do not guarantee that spacetime will have any of these three functions that he proposed. So they are, in some sense, entirely different. And okay, his argument was that even if spacetime has this theoretical function, it could still lack operational function. And he proposed some sophisticated example to it. My argument is much simpler, and it does not assume anything about this theoretical spacetime or theoretical function of spacetime in Tushar's terminology. I claim only that, at least in the context of special and general relativity, if one cares about chronogeometric significance, and if one thinks that this is somehow important for being spacetime, one needs to have this whole machinery starting from topological and differential structure in order to define some equations of evolution at all. Because without that, this wouldn't work. So if we agree with this classification with this special law of some functions of spacetime, that it indicates, then coming back to our very first question, one faces some important problem, namely this first group of functions that seems to be most important, at least in the context of standard formulation of special and general relativity. It requires that spacetime is a fundamental object, because everything else should be defined with respect to it in order to the whole machinery work. In particular, equations of evolution of matter should be defined precisely on this space-time, because without this, all these symmetries or all these causal considerations will lose their meaning. But on the other hand, this fundamentality is precisely what we wanted to avoid when we were proposing space-time functionalism as an approach that could help us to identify in, for example, quantum gravity theories, structures that represent space-time. So to this purpose, we should focus on group 2 and 3. But as I said, what about their meaning if we do not have this first group? How can we justify that they are still important and that they have physical meaning if we do not have this first group of functions, or at least something similar? So I do not have any particular example, but I suppose that we can face a kind of trade-off when trying to identify space-time in theories different than special and general relativity. So one way to do this was, as already described by me, so one needs to find in these theories an object that plays roles similar to these roles played by space-time in special and general relativity. And in this way, we obtain similarity of function between objects in different theories. Another way that as it seems to me, is actually used by physicists is to find a kind of isomorphism, or maybe some weaker isomorphism-like relationship between model of a given theory of quantum gravity and some model in GR, and this isomorphism or something weaker perhaps should be approximate and in some limit. The similarity we obtain in this way is called by me the similarity of structure. And one may ask whether these two approaches always give or even can give the same answer. And it seems to me that if we agree with the previous analysis of what similarity of function amounts to, then these two approaches can give different answer, because by using this structural approach, I will find some structure which is in some limits structurally similar to spacetime in GR. But this first approach probably will give me something different, will point out to something, to some more basic object, which is used to define the fundamental dynamics of the theory. So if this is the case, and if really these two approaches will give the same answer, they, of course, we would need to choose which of them is more important for us, which of them is better for finding in these theories something that we could agree to call the spacetime. So that's all. Thank you for the attention.
Thank you very much. Questions? Yeah, for sure, please.
First of all, thanks very much for the talk. And thanks also for focusing on where sort of you and I come apart. But I think in the spirit of sort of conciliation, I'd like to propose that maybe there isn't that much of a gap between what you're proposing and what I was talking about yesterday. So you spoke about you'll be interested in sort of an objective notion of space-time. And I contend that mine was sort of also objective, or at least sort of as subject neutral or subject independent. So, you know, in my case, both sort of theoretical and operational space-time both refer to sort of mind-independent structures. You know, theoretical space-time is just sort of a space of shared dynamical symmetry, features, and whatever. And in a sense, that seems to coincide with what you had in your third group, in your classification. So that was one point. I just have another quick, small comment, which is having a well-posed initial value problem on your approach doesn't mean that you're only committed to topological and smooth structure, because you also need the evolution equations to be sort of actual evolution equations, which means they need to be hyperbolic. If you're then thinking in sort of broadly dynamical Harvey-Brownish terms, then the fact that those evolution equations are hyperbolic will mean that you'll have to have some kind of time-space split on your manifold anyway. So in the case of special relativity, that will just give you a Minkowski manifold. In GR, it will give you a locally Minkowski manifold. In Newtonian mechanics, it will give you Galilean spacetime or whatever. So in that sense, on your proposal, you just get back to what I called theoretical spacetime. So I feel like there's sort of maybe not that much of a gap between what we. I mean, also just sort of if we as physicists, or at least philosophers of physics, we're interested in kind of identifying kind of objective types in the world or whatever, but maybe not entirely because we're only interested in what's there. It seems like the other purpose is to try to theorize efficiently, and that also seems like a kind of epistemic constraint. And so I think sort of all of those things together make me feel like maybe we don't actually disagree all that much.
Okay, thank you for your comment. So first, I should stress that I didn't want to impute you an subjectivist thoughts at all. But Okay, as I said, this maybe I am wrong, but if I understand this correctly, the motivation for your first two functions or spacetime is the spacetime should have this chronogeometric significance, and it seems to me that we bother so much about this because our theories of spacetime should have some empirical significance, and we want to make sure that spacetime, according to our theories, would be accessible for us by using our measurement devices. So still, maybe not in the content, but in the motivation, the crucial thing is the relationship between spacetime and spacetime theories makers, right? And in my approach, from the beginning to the end, the crucial relationship is between spacetime and any kind of matter. That's the difference. About your second comment, well, I wanted to understand this posing problem of evolution of matter in as broadly as possible. Okay, probably I should rethink what precisely I need to put into my spacetime in order to have what I want. But I do not want to think. Okay, this notion of evolution that I used has some very strong intuitive connection to evolution in time. But in conceptual elaboration of this concept, I wanted to avoid this. So for me, posing a problem of evolution would be also giving some constraints on distribution of matter in four-dimensional spacetime that cannot be split into space and time, even locally.
So we have 4 people. James, please.
Please, can you go to slide 16? Thanks. I don't think the situation is as simple as the advocate of the dynamical approach offering an explanation of the two miracles.
Okay.
Rather, I would understand the situation as follows. In the special relativistic case, it's a brute fact that all dynamical equations are locally or Lorentz invariant. So that's the first miracle. But we're to understand the Minkowski metric field as being a codification of those dynamical symmetries, so there's no second miracle for the advocate of the dynamical approach. Whereas in general relativity, it's still a brute fact that all dynamical equations are locally Lorentz invariant. But now we have an ontologically autonomous metric field, and that's the second miracle. Why should the symmetries of all of these dynamical laws coincide with the symmetries of the metric field? So in special relativity for the advocate of the dynamical approach, there's one miracle. In general relativity for the advocate of the dynamical approach, there's 2 miracles. In fact, it's the advocate of the geometrical approach that one might claim is able to, or is offering an account of these two miracles. They're saying that somehow the fact that we're dealing with a metric field of a certain kind constrains the possible form of dynamical equations, so there's nothing miraculous here. So I'm just saying that I would understand the situation a bit differently. In fact, it seems to me like the advocate of the geometrical approach is the one that is offering an explanation of these two miracles, whereas the advocate of the dynamical approach is saying that they're proof facts.
Okay.
Sorry, that wasn't really a question.
but I think that we don't disagree, but I use another word, and I would also say that a proponent of dynamical approach. Okay, so maybe like this. These two miracles are formulated from some, so to say, naive pre-interpretational point of view, and a proponent of dynamical approach resolves, in the context of special relativity, resolves the second miracle in a way that it disappears, something like this.
Yeah.
So I think we
agree. But they don't ever account for the first miracle, for example.
Great. Lorenzo, please.
Let me also thank you very much for your talk, especially because you try to describe what this role of space-time is supposed to be. So instead of so where I disagree, it was not going to be politically correct. That's not compared to what other people do.
I've noticed that.
So where I disagree, it seems that you include too much into the defining features of space-time. So I agree with your first one, and I think I understand what you mean by ontological approach, and I think that's exactly right. I think that you include too much. Possibly because, again, you take way too seriously what the famous people are saying. So I think that you said at the beginning, space-time is a framework for the description of the distribution and change of matter, and then you gave some examples in point 1. And I boiled down to something like, well, what space is a substratum in which particles can be located and fit their values. Right? You've made space something similar to what you said. Then you say something for time, and it's also a partial order, in which you study regularities, you try to see what guess, knowing what comes up before, what comes after, and that's all there is to space and time. I mean, maybe space-time is something that does both things, does both things at once. And that's it, right? The things about inertial frames seems neither necessary nor sufficient in space-time. So my question is, why do we want to include all of these things? Isn't the first point one sufficient?
Okay. My main idea was that okay, in some sense you are pointing to the direction that I wanted to go. Namely, I wanted to have a space-time as a minimal structure needed to pose the problem of distribution and or change of matter. Okay, but on the other hand, I have taken these two paradigmatic theories of space-time as my reference point. I wanted to list all the functions connected with the problem of evolution of matter that are played by space-time in these theories. And okay, I also wanted to refer somehow to the analysis of the space-time functionalism approach that were already in the market. So that's why I have said so much about inertial frames, not because they were important for me personally, but rather because I wanted to say that if for someone this role of space-time in special in general relativity is important, then such a person should notice I don't know, grounding relation of this function in some other functions of space-time in these theories.
So could you just say that you're maybe listing the function that it plays in GR rather than say what are predefined or this seems okay?
Yes, so probably I must two things. One thing is identify this minimal structure, and the second one is to list all the functions of space-time connected with evolution of matter that can be ascribed to space-time in these theories.
So, 2 more questions, 5 minutes. Eleanor?
Okay, so one concern, maybe actually I'll just say on the end of that, I think, at least my thought behind something like inertial frame functionalism is not that that's the most important function, it's that if you capture that structure, you're going to have captured, this is the kind of thing Harvey Brown argues for, if you capture that inertial structure, at least in a large class of theories, you're going to have captured lots of these other functions. So it's an actually useful thing that you can use to identify things in theories. And I think that you were worried about whether that was coherent. And I so there was a slide, let me see what number it was. There was a slide where you talked about, there's a slide where you talked, it was slide number, one was called inertial structures of function space-time, something like that. So you were concerned that you had to write, in order to understand the symmetry as this, you were concerned that in order...
the second one?
Yes, this one. There should be some equations of evolution that have these symmetries, and they should be formulated on the space-time that has this metric. That's quite a tricky business. There's 2 ways to formulate a space-time theory, right? One is in coordinate forms. You write it down in inertial coordinates. And that's the form in which the equations of the dynamics look like they have the symmetry. So if you're doing special relativity, you write down a coordinate-based theory of the equation, and those are the equations that are Lorentz covariant. There's a second generally covariant way to write down the theory, such that rather than writing down the equations of motions with explicit such that they have symmetries, you encode those symmetries in a coupling to the Minkowski metric. But of course, the first, in a theory like special relativity, we didn't need to know about the Minkowski metric to write down special relativity. Einstein had no idea about the Minkowski metric when he wrote it down. He wrote down a series of Lorentz covariant equations in coordinates. So it can't be right that in order to write equations with symmetries, we have to write them down on a space-time. It might be right that in order to write down equations with symmetries, we have to write them in coordinates. But writing them in coordinates is different from already writing it on a space-time structure. So I think this looked like one of your big concerns about the inertial approach, that it was, but I think it's actually the opposite way around. Once you make the space-time structure explicit, the sense in which you have evolving equations of matters with a certain set of symmetries becomes very attenuated.
Okay, so what can I say? So first, this idea that inertial structure is what is important for being space-time is for me far from obvious. So it seems to me that the best way to justify the importance of this structure is the way I described. So starting from something that I can intuitively agree that is the role of space-time in these theories, namely providing this whole framework to describe the matter. That seems for me very intuitive function, much more intuitive than providing inertial structure. But once we do this, we see what's the place of the inertial structure, why it is important. Coming to the inertial structure via this way was for me the only way to see its importance, and on the other hand, we should choose for a proper function of space-time something that makes it important part of our theories. So that's why I described it in this way. But of course, as I said, my problem was that if we abstract the inertial structure from this context, and if we believe that this whole way somehow gave the justification for its importance, then one could ask why should we care so much about this structure itself without this whole dynamical context.
Yeah. I don't think the claim should ever be that we should care about inertial structure without a dynamical context. That's not the claim. Is it's a shorthand for the kind of roles that you're interested in. So there's a conditional claim. If something describes inertial structure under certain circumstances, it will capture those roles. So you don't have to model them from scratch. That's the dynamical claim. Not that inertial structure is intuitively the most important thing.
Thank you. Maybe we should move on. And Chris, you can ask you a question over cooperation. So let's thank the speaker.